Hello, I'm Marian Keika, and this is the third design project for the Elec Eng 2EI4 course at McMaster University, and today is the 27th of March, 2024. The purpose of design project number 3 is to design, simulate, and build an amplifier that can take an input of plus minus 0.5 volts from a source with an internal resistance of 100 ohms and deliver it to a 100 ohm load featuring good linearity and less than 10% attenuation. As we can see from the circuit schematic shown on screen, the chosen transistor for this design was a bipolar junction transistor, also known as a BJT. The BJT was selected as opposed to a MOSFET for multiple reasons. And in our particular case here, we have the 2N3904 BJT, which is provided with in the 2EI4 component kit. Firstly, BJTs perform better in low current applications as opposed to MOSFETs. This provides a better benefit in amplifier circuits as they feature small variations within their input current, allowing for larger changes in the output current, meaning that a higher gain is achieved. Furthermore, upon comparing the amplifier stages of both the BJT and the MOSFET, we notice that the amplifier stage of the BJT is more linear due to the gain being independent of the bias voltage. Also, the BJTs feature a higher GM value compared to the MOSFET. This is due to the BJT being a current-controlled amplifier rather than a voltage-controlled amplifier like the MOSFET. Thus, irrespective of having a slightly higher power draw, the BJT can produce an output featuring a higher fidelity compared to the MOSFET. Finally, the BJT is simply faster than the MOSFET due to featuring a low capacitance on the control pin. These reasons make the BJT better suited for this application in this design project to satisfy the given requirements. And here we have the three common amplified technologies. We have the common emitter, the common base, and the common collector topology. These topologies each feature their own advantages and disadvantages. However, in this design project, the common collector topology was chosen for its characteristics. Since the common collector topology features a high input impedance, the calculated gain is found to be approximately 1, which aligns with the guidelines of the design project stating that the gain must be greater than or equal to 0.9. In addition, the allowed signal swing of the design project is to be 0.5 volts, which is considered to be very large, and the common collector, once again, works the best in this calculation. Here we have the calculations for each of the components in the circuit that we discussed previously in the design project number 3 for the 2EI4 course. So here initially we have the GM calculation using the formula 0.2 multiplied by V of t multiplied by 1 plus GM times RL is greater than or equal to VI. And we are given that the magnitude of VI is equal to 0.5 volts. V of t is equal to 25 millivolts at room temperature, and RL is equal to 100 ohms. Now, when we substitute these values into the formula, we can solve this equation to get that this inequality to get that GM is greater than or equal to 990 millisiemens. Now, utilizing this GM calculation, we can find Rin. We are also given that AB is greater than or equal to 0.9, and both RL and RS are 100 ohms. Now, utilizing the AB is equal to Rn over Rin plus Rs multiplied by Gm times RL over 1 plus Gm times RL formula, we can solve this and rearrange to get the value of Rin being greater than or equal to 1 kilo ohm. Then now to solve for R1 and R2, it's a little different as R1 and R2 can be chosen arbitrarily, such that we receive an Rin value that can satisfy this inequality here. So Rin is equal to R1 in parallel with R2 in parallel with Rn prime, where Rn prime is equal to R pi multiplied by 1 plus Gm times RL, where R pi is simply equal to Rs over Gm. So when we solve for R pi, we get that we have 100 over 990 millisiemens. Then as we plug this into the Rn prime formula, we will simply get 10.1 kiloohms as our value for Rn prime. Now when we substitute this in to the Rn equation, where we have R1 in parallel with R2 in parallel with Rn prime, we can select R1 and R2 arbitrarily as 10 kiloohms. And from this, we can see that our Rn value is found to be 3.34 kiloohms, which aligns with our inequality that we found previously. Also, the capacitance values were chosen arbitrarily as well, and they were both chosen to be 100 nanofarads, as these are two capacitors that we are provided with in the 2EI4 components kit. And here we have our finalized circuit schematic with all values inserted. Here is the circuit that we have built in LTSpice software. It was constructed using the various tools that are built into the software. We can see that in the circuit we have each of the components that were mentioned previously with their respective calculated values. Here we have the 2N3904 BJT that we are provided with in the component kit for this course. At the top we have the collector, which is connected to a 5-volt voltage source, which is then connected to ground. In AC analysis, this will become grounded, which mimics the common collector topology, where the collector is simply connected to ground. Now at the emitter, we have an R load resistor of 100 ohms, which is then connected to a negative 5-volt source, which is then connected to ground. We also have the emitter connected to a capacitor C2 of 100 nanofarads. In AC analysis, once again, we will be left with simply the emitter connected to the R load resistor, then connected to ground, which mimics the common collector topology. At the base, we have two resistors placed in parallel, R1 and R2, both of 10k ohms. They are both connected to ground. They are then connected into C1, which is 100 nanofarads. Then we have an R source resistor of 100 ohms. Then we have an input voltage, which is a sinusoidal waveform of 0.5 amplitude, 0.5 volt amplitude, with a frequency of 10,000 hertz. The 10,000 hertz is selected to improve the results of our simulation, and a transient analysis was performed on this circuit with the default settings as shown here. However, the stop time is changed, in fact, to 0.001, as an increase in the frequency will result with many oscillations in the output graph. Thus, the stop time must be changed to reduce the amount of oscillations to make it easier to analyze the graph. Now, as we can see in the output graph, we can see that the input voltage is here in green, the output voltage is here in blue, and we have the current shown in red. The two graphs of the input and output both overlap, which assumes linearity, which is desired in our design. Upon further investigation, we can notice that the input voltage is found to be approximately 500 millivolts, and the output voltage is approximately 465 millivolts. And these are both the max peak values for both input and output. Now, using these values, gain can be calculated as shown here, where AV is equal to V out over Vn, which is equal to 0.466 volts over 0.5 volts, which gives us a gain of approximately 0.932, which is greater than or equal to 0.9, which is the desired specification. Now to find the input resistance, we use Ohm's law, which is V equals IR. We rearrange this equation to get V over I. And again, we just use the V input, which is 0.5 volts. And then to find 112 microamperes, we simply analyze the graph again, and we can see the current in red here. If we go across, we will find it to be approximately 112 microamperes. Now, upon performing this calculation, we can notice that we get an input resistance value of 4.1 kiloohms, which is much greater than the 1.9 kiloohms desired specification. Thus, this concludes that the simulation is correct.
Here's a physically built circuit, and we will go over it from left to right. Here, this yellow wire here is the input sinusoidal voltage. This orange wire here is positive channel 1, which is used to monitor the input voltage. And just right here, we have, right next to it, here we have a 100 ohm resistor. Then to connect it to that, we have the 100 nanofarad capacitor. Then connected to the nanofarad capacitors are the two parallel 10k ohm resistors. We also have this green wire here, which connects the node connecting the two parallel resistors and the capacitor to the base of our BJT. Then the two ends, both ends of the two parallel resistors are simply connected to ground with this black wire. Then over here we can see that this red wire is the positive 5 volt input, which is here at the collector. Then here in the middle, we again at the base of the emitter, we have the green wire, which is just connecting the base. Then here at the emitter portion of the BJT, we have both the 100 ohm resistor and the 100 nanofarad capacitor that are both connected. The capacitor is then connected to this blue wire, which is the positive channel 2, which is used to monitor the output voltage of our amplifier circuit. The 100 ohm resistor is then connected to this white wire, which is connected to the negative 5 volt input. Then we have this blue wire here, which is the negative terminal terminal of channel 2, which is simply connected to ground. This orange one likewise is negative channel 1, and then this black wire is simply the ground connected to the 82. Then here is a close-up of our BJT, where as we can see in the middle we have the base. Here on the right we have the collector. Here on the left we have the emitter.
We can see here on the screen that we have the supplies. We can see that in the positive supply, we're supplying a positive 5 volts, and the negative supply, we're supplying negative 5 volts. Now here in the wave generator, we can see that for the input voltage, we have a sinusoidal waveform of 10,000 hertz with an amplitude of 0.5 volts. This matches the input voltage that was used in LT-Spice for the simulation in that. Now here in the scope, as we run the scope, we can see in blue we have the output voltage, and in orange we have the input voltage. If we were to pause this, we can see that here in the measurements tab, we have a maximum for C1, a maximum for C2. This is the max peak for both voltages. We also have a peak-to-peak value for both of the voltages. We also have the frequencies of both, and we have an average. This is a custom math function that is C2 over C1, which is used to calculate the gain, because C2 is the output voltage, C1 is the input voltage. If we divide the two, we will get the gain. So either value could be used, the maximum could be used, or the peak to peak could be used to calculate the gain. Both would end up with the same result. However, here we run this and we will get an average gain with the C2 and C1 values. So here in this run, the average gain was calculated to be 0.98, which is above the minimum gain of 0.9, which is mentioned in the project specifications, and it also aligns with the gain that was found in LT Spice. So to determine the linearity of the circuit, we first noticed that the overlapping of the two graphs is present here as well as it was present in LT Spice. This overlapping does once again assume the linearity. However, the linearity can also be determined through two other methods. First, using the spectrum, we can see here in the spectrum analyzer that the signal strength for both input and output voltages are relatively the same, which expresses linearity. We can also take a look here at the scope, and if we went here in the wave generator, if we change this 500 millivolt amplitude from 500 to say 200 and we ran it, our gain calculation will be relatively the same as it was previously. This also aligns with the idea of linearity as the gain does not change with a change in the input voltage from the magnitude of 0.5 volts. Now here, once again, we're just going to compare the gain calculations from both LT-Spice and waveforms and then do a quick percent difference calculation. So the gain calculation from LT-Spice was found to be 0.932, which is greater than our given 0.9 or given base requirement of 0.9. And now the gain calculation of waveforms, we selected 2 points on the graph that were found to be 0.498 and 0.5 volts. This provides us with an output gain of 0.986, which again is above the minimum spec. Now if we take the percent difference between these two values, we have V1 minus V2 divided by V1, the sum of the two values divided by 2, all times by 100. When we perform this calculation, we get that the difference between the two gains is roughly 5.6%, which is accurate and concludes that we have successfully completed the project.